In this lab, we'll be conducting an acid-base titration of a polyprotic acid using some sort of strong base. And so I wanted to go through and discuss conceptually how we can think about what is happening at each point in this polyprotic titration curve and what species are present and how that influences the pH at various points. And so in our lab, we will be using triprotic acids, which would be represented by an H3A, but we're going to use H2A, a diprotic acid, just as the example for this background explanation. And so every weak acid, of course, has a different pKa value, and this H2A species will interconvert between H2A, HA minus, and A2 minus over the course of this titration. So initially, we make the solution out of the fully protonated acid, H2A. This would have the lowest pH, the most acidic pH out of any of these species, because it is the strongest acid out of any of these species. So that would mean that it makes the most H3O plus in solution, depending on the relative size of its Ka value. I'm not going to put values on our pH axis or on our volume of strong base, but essentially we're slowly adding strong base so that we could observe the point at which we exactly convert all of the H2A into HA minus, and again, the point where all of the HA minus is converted completely into A2 minus. And we can use this technique both to identify the acid based on the pKa values determined from the plot, but also to determine the concentration, and that's the most typical use of titration, the concentration of the acid in solution. And so if we knew the concentration initially, it would be possible for us to calculate the pH at various points. Because we won't know the concentration initially, you're going to have to measure the pH at various points. And so we will use a pH probe to measure the concentration and to measure the pH at various points. So let's just say we're starting out with our titration curve and the pH is somewhere around this point initially when we have just the weak acid in the fully protonated state. We start adding some strong base, and we'll start out by initially having a slight uptick in pH because all we have is this weak acid in solution. But as we reach the point where we're starting to have a mixture of weak acid and its conjugate, which would be HA minus, we'll actually start to kind of plateau for a little while. And that kind of region we'll discuss in more detail is due to the fact that we are in a buffer region. There will come a point, though, where we start to increase in pH again, and then we get a sharp increase. The middle of that sharp increase represents our equivalence point, and we'll talk about that. That equivalence point is exactly when our H2A has converted into all HA minus. So exactly however many moles of H2A there were, now we have that many moles of HA minus. And we use that information based on the concentration of our strong base that we're titrating with to determine how many moles of H2A must have been in the solution to begin with. All right, so we'll continue on. You continue adding strong base, and your sharp increase starts to level off because now we've moved to a point where we're starting to generate some mixture of A2 minus and HA minus, and so we'll see another more plateau sort of region, which again, this is going to represent a mixture of conjugates again, so we can call that another buffer region, mixture of two conjugates of one another. As we keep adding more base, we will eventually start to leave that plateau region and get to a sharp uptick in pH again, where we will find the second equivalence point. The equivalence point in this case represents all of our HA minus, every mole of it being turned into A2 minus. And so that can confirm again the number of moles of our weak acid that we must have had initially in solution. So at the very end here, we'll start to kind of level off again because we're getting to the max pH of the scale, and also it depends on how strong the base is where the final curve will end up. But this is what you should observe for a polyprotic titration curve. The number of sharp inflection points is related to the number of protons on your weak acid. So however polyprotic it is will determine how many of these sharp inflection points we find in the curve. So that means for our lab, if we're using a triprotic acid, you should see 3 of them, although sometimes they're very close together and they may not be very obvious. So we'll use a data analysis strategy of taking derivative at each point to try to see little peaks to represent that sharp inflection point. All right, I'm going to go through kind of more of a visual model to explain what's happening at each point. So remember initially in our titration, we had just H2A in solution, and I'm going to call this initial. And at the initial point, our pH we could determine from an ice table, just like we do for any weak acid. All right, and that weak acid would be our H2A. So we would need the Ka for H2A to be able to do that ice table. All right, so that would be before we add any strong base. After we've started to add some strong base, we get into the buffer region. And right in the middle of that buffer region, we have our half equivalence point, which we'll define in a moment. But to describe the pH at any point in our buffer region, if we knew the relative concentrations of HA minus and H2A, we could determine the pH, but we would need to use the pKa of H2A at this point in order to solve for pH, because the acid in our context at this point is H2A, and HA minus is more like a conjugate base. Okay, so moving on from there, once we get to the point where all of our H2A has been converted into HA minus, now we're going to have HA minus reacting with water, and there's 2 real possibilities here. HA minus could have a larger Ka value than Kb value and therefore act as an acid. In that case, we would form H3O plus and A2 minus. The alternative is that the Kb is actually larger than the Ka, so it therefore acts as a base, and in that case, it would form OH minus and H2A. So you would actually have to know something about the potential Ka values in order to determine whether it's going to act as an acid or base in this instance. This is our equivalence point, like we already mentioned. This is the important point on the plot to determine the concentration of H2A, or the weak acid in solution. So our pH at this point is going to be actually based on an ice table of our diluted, because remember we have added solution at this point. So now our total volume is larger, so the concentration of the conjugate base in solution is lower than what the original weak acid was. And this is going to be of our first conjugate. So I'll call it first conjugate just so we know what we're talking about. That would be HA minus. And so that means that you need to use either the Ka or Kb of this compound, HA, depending on whichever is larger. That will determine whether you do it as a more acidic ice table, producing H3O+, and you can directly get your pH from that, or whether it's a basic ice table and you get OH concentration, so therefore you have to do some manipulations to get to the pH. All right, after the first equivalence point, again, if we recall in our plot, we keep adding base and it gets to another point of leveling off. And that is because now we have a mixture of HA- and A2-, which is our second buffer region. Okay, in our second buffer region, we can describe the pH at any point there based on the ratio of A2- to HA-, but the pKa we would use at this point is the pKa of HA-. So shouldn't be too hard to calculate a pH here, but remember our concentrations are diluted, so you'd always have to keep that in mind. All right, we get to the next point where now all we have in solution is A2-. This is our second equivalence point. All right, so at this point, for us to be able to determine the pH, we would need an ice table of our diluted. Remember, we've added even more solution at this point, so the volume is even greater. And I'm going to call it second conjugate. And write what that is, just so we remember, A2-. And so that means that we would need to use the Kb. And the reason it's not Ka or Kb for this one is because there are no more protons to donate, therefore it cannot act as a Bronsted-Lowry acid. It must be acting as a base. So we're going to generate hydroxide in solution, and we'll use the concentration of hydroxide to figure out either POH or hydronium concentration and go from there to get to the pH. All right, so the last section of our graph, remember after our second equivalence point, we increased and leveled off again at a very basic pH. And that's because at this point now we've added so much strong base that we have free-floating hydroxide that's not coming from our weak base, just coming from the strong base. So however much excess hydroxide we've added at this point is just hydroxide concentration in solution. So this is excess OH-, which I'll use to stand in for my strong base. So the pH we will determine based on, we can take the Kw and divide by the hydroxide concentration. I'm going to say diluted because I'm going to say diluted and reacted, because remember, a significant chunk of the hydroxide we've added has reacted with acid. So you have to subtract all of that out, 2 mole equivalents worth of the hydroxide that is now added at this point has been reacted with our weak acid, because our weak acid had 2 protons that completely reacted with it. Also, any excess we're adding now is going from the initial concentration of the strong base to our diluted solution of our total volume in our flask. So that's why I put those notes there just as a caveat. So if we do Kw divided by concentration of hydroxide, that gives us concentration of hydronium, so that's why that's here. And negative log of concentration of hydronium is what gives you pH. So that's how we would determine pH at that point. All right, so from here, let's define a couple of terms briefly. The equivalence point is the point where moles of strong base equals moles of weak acid. in the solution. Okay, so we have 2 equivalence points in a diprotic. So at the second equivalence point, we will have added twice as many moles of strong base as the number of moles of weak acid in solution, because there are 2 protons to remove. Hopefully that is made abundantly clear. And then we have our half equivalence point. This is the point where H2A to HA minus, or HA minus to A2 minus are 1-to-1 ratios. Therefore, according to our Henderson-Hasselbalch formula, pH equals pKa. So that information is crucially important to matching it up with a possible candidate. In our experiment, you're not going to know whether you have citric acid or phosphoric acid in your soda sample, so you will need to look at these half equivalence points to determine how close those pH equals pKa values are to the known pH equals pKa values for citric acid and phosphoric acid, just as a little bit of introduction. All right, the last thing I have here is just a little bit of an explanation of how a typical acid-base titration would go. So typically you have a burette, and most often you're going to be putting your strong base in your burette, and this has a known concentration. That is also true in our case. It doesn't have to be a weak acid for an acid-base titration, but we are using a weak, and in this case, polyprotic acid. So I'll just add that for some context for us. All right, and this is an unknown concentration. This is the most typical use of a titration. We want to measure the concentration of what is in the flask below. We start adding drops after we have added an indicator. And in this experiment, we will not need an indicator because we'll be able to see our equivalence points on the pH plot. But typically, you would add an indicator to tell you when you've reached the equivalence point. And the selection of the indicator is dependent on kind of Ka properties, what range you would expect your pH when you reach the equivalence point. That would determine what type of colored molecule you would select. So the idea of the indicator is that at one pH range, it's one color, and then you get to another pH range and it shifts colors. And you want that shift of color to occur right when you are reaching the equivalence point. So that is something that you have to design when you're determining how to set up this type of experiment. But we won't be worrying about that. But this example here, from clear to pink, when it gets more basic at the equivalence point, that is a typical phenolphthalein indicator that you may have used in the past. All right, so just a little bit more detail about this actual experiment. So you'll be given, or actually you'll select as a group, an unknown soda sample. And your unknown soda sample could have either citric acid or phosphoric acid. Sorry, my handwriting. Okay, so you don't know which one is there. They're both triprotic. All right, and at that point, you as a group would look over the research questions and think about what the goal of each research question is. The first goal is essentially determine the polyprotic acid identity, i.e. is it citric or phosphoric? And you're given Ka values for each of the protons in each of those compounds to compare with. Then you will also determine whether that concentration of polyprotic acid is in an acceptable range for quality control purposes of these soda samples. So you're given kind of a typical range that you would expect that concentration to fall under. So you're going to have to measure the concentration and determine whether it is inside or outside that range. As a soda quality control analysis specialist, that's your role. All right, so the tasks involved in the experiment are that initially you and your group would plan a triprotic titration procedure after you have selected your sample. You will carry out that procedure and collect your own data, so you'll have to decide like how to set up your tables, how much you should depend on the digital data versus how much you should actually record. And I strongly recommend recording as much as you can as you go, so that even if something happens to digital data, you have it. So that can be one person's job, but you'll have to negotiate who's doing what. Then you will, as a group, analyze your data kind of from a general standpoint. And later on, you'll go through and do more of a numerical analysis with the guidance of data worksheet. But you'll set up a group argumentation about both research questions. And so you'll have to do enough analysis to be able to answer both research questions, i.e. calculate the concentration and determine which polyprotic acid you have. And after you have done that, you can compare with another group. And the value in this is that you can kind of see how other people have worked through this analysis and see if what you did is reasonable, or even give another group the feedback so that they can get more on track with how they have analyzed their data. So that is overview of this experiment.